analysis, also known as a titration. It is a fundamental quantitative technique in analytical chemistry in which the concentration of unknown substance is determined by measuring the volume of standard solution required to completely react based on stoichiometry. Determining glucose concentration is very important in medical diagnostics and biochemical research, as glucose functions as the primary energy sources for cell and is a key indicator in metabolic disorders such as diabetes mellitus. Artificial blood systems are now increasingly used in experimental setup to mimic the chemical and physical properties of real blood, while avoiding biological risks and ethical issues, better control of experimental variables, and improve the reproducibility of results. By applying volumetric titration to artificial blood, the volume of the titrant required to full react with glucose in the sample can be accurately measured, allowing the glucose concentration to be calculated based on non-stoichiometry relationship. This method is highly suitable for use in educational laboratories and research environments because it offers simplicity, low cost, and requires only basic laboratory equipment. Moreover, it has the potential to be adapted into modern formats such as microfluidic platform or point-of-care diagnostics.
Okay, now we look for the theory. First, we look for the principle. It is using sugar, for example glucose, reduce 3,5-nitrosalicylic acid (DNS) to 3-amino-5-nitroxylic acid under alkaline heated condition. Now we look for the procedure highlight. First, we prepare the glucose standard and unknown, add DNS reagent, heat in a boiling water between 5 to 50 minutes, and then add stabilizer, for example sodium tartrate. It's also to measure the absorbance spectrophotometrically. It typically at 540 nanometer, and the color development for the yellow DNS is converted to an orange-red color product. Color intensity is directly proportional to glucose concentration, and for the advantage and limitation, it's simple, cost-effective, and rapid method. It's also less specific. Other reducing substance can interfere, and also proper blends are essential. Now we look for the key equation. DNS reaction simplify, reducing sugar plus DNS become amino-nitrosalicylic acid. It's show red-orange complex. For the standard equation, we use Beer-Lambert law. And now we look for the quantification. A standard curve, absorbance versus concentration, is created from the non-glucose solutions, and unknown are interpolated using the curve. Result from the article, sample A shows 0.0163 mg per ml, and for the sample B, it shows 0.00426 mg per ml.
Methodology in this experiment: first apparatus is test tube, pipette or micropipette, measuring cylinder, vortex mixture, parafilm, water bath, cuvette, UV spectrophotometer, labeling material. Chemicals is glucose, stock solution, DNS reagent, which is 3,5-nitrosalicylic acid, distilled water, unknown glucose solution. First of all, preparation of a test tube. 6 test tubes in set A were labeled 1A, 1, 2, 3A, 4A, 5A, and 6A. 6 test tubes in set B were labeled 1B, 2B, 3B, 4B, 5B, and 6B. 2 test tubes with unknown glucose concentration were labeled with set A and set B. Second, addition of glucose standard and unknown glucose. 1 mg per ml glucose stock solution was used. Volumes of 0.2, 0.4, 0.6, 0.8, and 1 ml were added to test tube 2A and to 6A and 2B to 6B respectively. Tube 1 in both sets was left blank, no glucose added. Tubes SA1, SA2, SB1, SB2 were filled with 1 ml of unknown glucose solution. 3. Volume adjustment. Each test tube was topped up with ultra pure water to a final volume of 1 ml. 4. Addition of DNS reagent, which is 2 ml of DNS reagent was added to each test tube. Step 5. Mixing. All test tubes were mixed thoroughly using a vortex mixer. Step 6. Heating. Tubes were sealed with parafilm and heat in the 90 Celsius water bath for 5 minutes. Step 7 is cooling, which is each test tube was topped up with ultra pure water to a final volume of 1 ml. Egg dilution. 7 ml of distilled water was added to all test tubes except the unknown solution. Step 9. Second mixing. Tubes were vortex again for uniform mixing and transferred to cuvette. 1 ml of each solution from tubes A1 to 6A was transferred to label cuvette 1 to 6. Unknown sample SA1 and SA2 were also transferred to cuvette. This was repeat for set B. 10. Absorbance measurement. Cuvettes were placed in a UV spectrophotometer. Absorbance was measured at 540 nm. And lastly, repeat for step B. Step 9 to 11 were repeat for step B sample, and the average absorbance reading were calculated
by using a pair of redox reactions. To begin, we have aliquoted a known volume of our glucose solution into a flask. To this, we will add reagents for the redox reaction to proceed, and then follow this up with the titration. As you will be timing multiple reactions in this lab, you may wish to prepare each reaction mixture in advance in a small beaker. This way you can add them all at once and simplify your timing. The reaction mixture is composed of triiodide as well as sodium hydroxide. The triiodide needs to be added quantitatively, whereas the sodium hydroxide can be added in rough quantities using a graduated cylinder. The two reagents may be mixed prior to addition to the glucose solution without any detrimental effects. If you have prepared your reagents in a beaker as I have shown, you will need to quantitatively transfer the solution. Therefore, you will need to rinse out your beaker and transfer the remaining reagents into the flask. You will now let the reaction proceed for approximately 5 minutes. In this time, prepare your hydrochloric acid to be able to quench the reaction when the timing is done. The amount of hydrochloric acid does not need to be measured with great accuracy. Using a graduated cylinder is acceptable. For your first titration, you may wish to do a rough titration to get an approximate endpoint. If you are doing this, you will want to add the starch indicator immediately at the beginning of your titration. For the accurate titrations that you will use for your quantification, you will want to add the starch indicator significantly later. The reason for this is that starch can permanently bind the triiodide molecule and may lead to difficulties in visualizing the endpoint. As you will see through this titration, the initial color of the solution is a golden yellow. As you proceed through the titration, it will become lighter and lighter to an almost pale yellow color. When you've achieved the pale yellow color, it's time to add the starch indicator. The indicator will greatly change the color of the solution, making the visualization of the endpoint much easier. As you can see, the addition of starch turns the solution to an almost black-blue color. This color will disappear and become completely colorless when you reach your endpoint. As with all titrations, it is important to swirl the flask continuously to ensure that the reaction is proceeding. In addition, rinse down the walls of the flask on occasion to make sure that no reagent or titrant is clinging to the walls. This analysis is unique in the fact that we are using two reactions to quantify the amount of glucose in solution. The first reaction is between glucose and triiodide. Glucose is a reducing sugar and will lead to the reduction of triiodide. We have added an excess of triiodide to the solution. Therefore, when all the glucose is exhausted in the reaction, excess triiodide will remain. This triiodide is then quantified by the titration with thiosulfate. As we know the concentrations of thiosulfate and triiodide, we can determine how much triiodide was used in the reaction with glucose and determine the amount of glucose as a result. If you have not added your starch indicator too soon, it should be very easy to see a clear transition to a colorless solution for the endpoint of this titration. Ideally, you should be able to achieve this with a single drop of titrant.
Now, let's look at the results and calculation for tubes 1 to tubes 3. We are preparing different concentration of standard glucose solution from an original stock concentrations of 1.0 mg per ml. The formula used is M1V1 equals to M2V2, where the M1 is the initial concentrations, which is 1.0 mg per ml. V1 is the volume of the stock solution used. V2 is the final volume, which is fixed at 10 ml. M2 is the final concentrations. For tube 1, no standard glucose is added, so concentration is 0.0 mg per ml. For tube 2, we use 0.20 ml of stock solutions, so we calculate it as 1.0 mg per ml. We'll multiply 0.20 ml and divide with 10 ml and equals to 0.02 mg per ml. For tube 3, 0.40 of stock solution is used, so 1.0 mg per ml will multiply 0.40 ml and will divide with 10 ml equals to 0.04 mg per ml. Okay, moving on to tubes 4 to tube 6. So, we continue increasing the volume of standard glucose. For tubes 4, 0.60 ml is added. So, calculation is 1.0 mg per ml multiply with 0.60 and divide with 10 ml equals to 0.06 mg per ml. For tube 5, we use 0.80 ml of the stock solutions. So, 1.0 mg per ml will multiply with 0.80 ml and will divide with 10 ml and equals to 0.08 mg per ml. And finally, for tube 6, 1.00 ml of the standard glucose is used. So, the calculation is 1.0 mg per ml will multiply with 1.00 ml and will divide with 10 ml and will equal to 0.10 mg per ml. As you can see, we are gradually increase the concentration of glucose in each tube for adjusting the volume of the stock solution.
Now, to summarize, the volumetric determinations of glucose concentration in artificial blood was successfully enabled by the Starch-Iodine titration method. Through the reactions between glucose and iodine in an acidic medium, as we can see in the results, the amount of glucose present was identified based on the volume of iodine solutions required to reach the endpoints. The Starch-Iodine titration method is a great choice to determine the glucose concentration in artificial blood because it is simple and cost-effective, also sensitive to glucose concentrations, and suitable for artificial biological samples.